been a year of self-paced systems.
Yeah,
I'm very glad we got some cheers. It would have been sort of awkward if I said that and it just kind of silence, and then I would feel kind of underappreciated, as if this is an extension of myself. So if it's your first time, we're a nonprofit independent tech talk series. Remove that mouse cursor, that's extremely annoying. We sometimes host casual coffee chats, however, it's been actually quite a while. There's no affiliation to any company or product, so the talk is not affiliated with Snowflake, just hosted by Snowflake and sponsored by Snowflake. We're monthly-ish, although we've been fairly consistent recently. Here's hoping it stays that way. We're focused on systems programming in a pretty broad definition. Systems, that could be, that's on a later slide. Organizers, here's some past talks. Lots of really good ones. Watch the recordings if they're available. Yes, computer systems. Anything in any of these areas, or even sort of branching off from that: networking, systems at scale, operating systems, databases, compilers, security, hardware, verification, testing, anything computer systems related, please sign up here. Yeah, we want more talks. We love organizing talks. Thank you to Snowflake for hosting, which I also happen to work at. If you have space for 50 plus people and can sponsor food and drinks, or one and not the other, or the other and not the one, then please reach out and let us know so we can maybe host a talk at your office. Thank you to Snowflake. Usually we have a recruiter come up and give a little pitch about how great the company is, but nobody's here. It's just me. I'm an engineer. So I don't know, come work at Snowflake. The best pitch I can give is that they give me work that I feel I have no business doing as someone who just started, which I think is excellent. So please come to Snowflake, and then I can have more friends. All right, so we have two speakers today. We have Sugu, the head of Multigres, co-founder of PlanetScale, co-creator of Vitess. I never pronounced that out loud, actually. Vitess. There we go. And then afterwards, we'll have Stu Hood, head of engineering at ParadeDB. And yeah, these are going to be awesome talks. So give it up.
Yeah.
You want to do mirror display, you can do extended if that's better.
Extend is better?
Whichever one you prefer.
Let's do extend.
Okay. So. Just close this.
Oh.
Yep. Okay, and then so that's your extended display. Put whatever you want to present up there. Maybe the other direction. There it is. So that's what that's what's visible up there, if that's easier to look at.
Okay.
Okay, and here's your clicker if you need it.
This is awkward because left is right. Okay. Good evening, everyone, unless you came from a different time zone. Can you all hear me well?
Yeah.
Okay. Today, I am going to be talking about a generalization of consensus. When I came, people are asked, I said, like, I work at Supabase. Are you going to be talking about databases? Are you going to be talking about multigres? And says, none of the above. No, I'm going to be talking about something very theoretical of some sort. This topic is so complicated that it will take me 5 days to explain. And no, Alex told me you only have 30 minutes. So I'm going to cram it all in. So I guarantee you, you're going to be disappointed because I won't be able to go through everything that I wanted to go through. So what I'm hoping to do is, point you to the right way and then go fish for yourself about any further information that you need that you can get from multigres.com. So if you go to multigres.com and hit the blog button, and you will see a bunch of talks here. This is an 11-part blog series that explains what we are talking about in terms of generalization of consensus. So that is just in case at the end of the talk, you have lots of questions and we don't have time to go through. Ben told me that I have a little bit of wiggle room in terms of time, so I'll try to go slightly slow and we'll see where we land. So let me go to start the slideshow here. Okay. Consensus. What is consensus? Any opinions from the audience? Anyone has?
51% of the people who agree.
Majority agreement. Okay. Anything else? Any other thoughts? Without a leader. Okay. So that's one form of consensus, although most consensus protocols have leaders.
Like Raft.
Like Raft. Yeah, Raft. There's a hand raised here.
The variable has one value.
One value.
Consistency requirement.
Consistency. Anything else? Okay, that's good enough. I guess there's one term that I've heard that that people have told me is agreement. I guess one value is agreement. Right? So that's one of the things. So it was kind of a misleading question because the way I would put it is if you asking the right questions is important, but it's also defining the problem well. So let me turn the question around and ask you a different question, which is, so this basically, if you define the problem correctly, you almost have the solution. I found this on the internet. I don't know if Steve Jobs actually said it, but this is true, okay? So, so let me ask you a different question. What are the use cases for consensus? Why would you use consensus? Any opinions, thoughts? Fault tolerance, okay. Distribution, okay.
Incognito robot swap.
Incognito robot swap.
Coordinate a robot swarm.
Oh, robot swarm. Coordinate a robot swarm. Wow, cool. Yes.
I was thinking along the lines of to solve a problem, you can get enough to agree over 51% and you can solve that.
Okay. Okay. There.
Security to have attestations.
Maturity, is that what you?
Security.
Security. Okay. Okay. Wow. I did not expect these answers. Okay. And what's that one?
To read what you wrote correctly.
To read what you wrote. That's actually a consistency property. Okay. Here.
Sharing configuration.
Sharing configuration. Okay, that's a functional requirement.
Sharing topology.
Sharing topology, which is what consensus is used for, HCD. Anything else? Convergence? Ah, that's a good one. That's a good one.
Ultimately, to resolve conflict.
To resolve conflict. Okay. All right. I think we'll keep on having opinions, but I have an opinion which is not everything which I didn't hear in the room. I was hoping to hear it, which is consensus main use case is durability. If you look at history of software, until 2000, even though until 2000 or so, when did 9/11 happen? Until 9/11 happened, durability was considered, if data went on disk, it was considered durable. And after 9/11, they said data going on disk, durability is insufficient. For something to be durable, it has to be in more than one location. And that's when the first time they tried it, it didn't quite work. And then they looked for papers. They found, Paxos and so that's actually the first problem that I believe consensus solves, the most important problem. And it's not just durability. The other thing that it solves is availability, which means that if there is a failure, you want the system to continue to operate. So that's availability. And this one I did here in the room, which is consistency. But I want to be a little more precise here. When you talk, consistency means many things. In consensus, the specific consistency problem that it solves is actually the opposite of convergence, which is split brain. So if you write data in multiple places, how do you make sure that, if there are failures, and then you work with a subset of what is left over, the entire network doesn't become inconsistent, right? There is no split brain in the network. So that is a problem that consensus solves. Because no matter what kind of failures happen, it'll keep all the nodes together, agreeing on the decisions. There's actually one final property of consensus that we implicitly assume and know, but never state for ourselves, which is every system is built for tolerating certain level of failures. If that tolerance is exceeded, what should happen to the system? Like, for example, there's 3 nodes consensus. If 2 nodes have failed, what should the system do? Right? And usually the answer is, well, it should refuse to accept any more transactions. If it continues to accept transactions, then it means that it is not satisfying its important properties, which is durability and availability. Well, actually, it gives up availability to preserve durability. So the reason why I asked this is because if you start with consensus as an algorithm and then apply it to solutions, sometimes there is a mismatch because the algorithm was not built for the solution. So now what I'm going to do is actually turn the problem around and saying that, let's not worry about the algorithm. Let's identify what we are trying to solve, and let's see what we come up with. So that is going to be what I'm going to attempt today, and let's see how far it goes. So I'm going to actually kick out consensus. If any of you know about consensus, leave it outside, and we'll start from scratch. So if we are going to solve durability, what is it? It's not just durability, it's distributed durability. What is the functionality? How do we describe that functionality? This is how I would describe it, is a consensus system that solves durability. What it should do is if I'm a node and I receive a request, my job is to make sure that that request goes somewhere else, not where I am. And once it has gone somewhere else, I can tell you, okay, I won't lose your data no matter what. So that is distributed durability, which is what disks were supposed to do until 9/11. Then they failed. And the second part of this is, if I happen to fail after I've said, I've accepted your request, given it to my other nodes, and then I said yes, and then I fail, then what I have to guarantee is that the system needs to reconfigure itself and make sure that that data is not lost. So that is my layman's definition of consensus. So if you look at this, right, there's no mention of majority quorum, nodes agreeing, etc., etc. This is what consensus should do, in my opinion. And if a product manager came and told me, let's assume a world where Leslie Lamport did not become a professor in computer science. Instead, he went and did some theoretical physics or something. So today we will not have Paxos or Raft. But then this is still a need. If they came and told me, build a system that does this, then I'll have to build it from the ground up. Right? So that is what I'm going to attempt. It takes many years to come up with this, but I'm going to try and do it very, very fast. So in this, I use the term called elsewhere. What does elsewhere mean? It is intentionally vague. Why is it intentionally vague? It is because elsewhere is a user-defined constraint. Right? Every person's, their durability requirements are different. Like if I'm a bank, I want my data to be, very far away or in at least 5 places, whatever, right? Like the first thing is, there's no such thing as, absolute no data loss guarantee, because if you lose all your hardware, you've lost all your data. But you can say that, if data is in at least these many places or these locations, I'm happy. So that is your durability requirement, right? And the consensus system has to give you that. So elsewhere is user-defined. And therefore, let's actually talk about some examples, right? I may say, I want 5 nodes. And when I give you a request, if that request goes to at least one other node, it's good enough for me, right? Or I want 10 nodes. If it goes to at least 2 other nodes, it's good enough for me, right? So that's a reasonable requirement. Here's another, this is a very common one, right? You are on AWS, you have availability zones, and you have nodes across availability zones. And you may say, as long as my data goes to a different availability zone, I'm happy, right? And then what if there are 4? How would you configure Raft to work on 4 availability zones? Interesting question. Here's another one. This is actually a real one from an enterprise customer. They have only 2 zones, 2 data centers. They have a primary data center, a secondary data center. And for them, secondary data center is mainly for failover when there is a disaster. So if there's a problem, they fail over to the secondary, live on the secondary, rebuild the primary, and then migrate back to the primary. So that's how they operate. So we can keep going. So what is common across all these problems is that Raft or Paxos are not well suited to solve these. That's why I selected these. But these are real requirements coming from the field. Okay. So in other words, there's one major problem with existing consensus protocols is that they are all majority quorums. But when I say all, it's mostly Paxos and Raft. I don't know how many of you have heard of FlexPaxos. Cool. There's a few. FlexPaxos was actually the first algorithm that said that, and you too, yeah, that said that no, you don't need a majority quorum for consensus to work. Okay, so that's one problem that generalized consensus says. Okay, you don't need a majority quorum. The other one is, which is the reason why I have been passionate about it, is algorithms like Paxos and Raft are black boxes. They are very magical, as in you don't touch them. It just works. But you cannot adapt them to something else. You cannot say, okay, in my case, I wanted consensus for Postgres, right? And today Postgres doesn't have a consensus protocol, and Raft and Paxos are not usable, right? Now the question you ask is, how do you break it up? But in order to break it up, you have to understand what you can change and what you cannot change, right? If I took this part out and moved it out, will it still work? Like, how do you prove that it works correctly, right? So that is what we are going to do. So in other words, what we are going to do is decompose consensus. Or how do I state it? We are going to conceptualize it, and I'm going to do a big reveal for you. Believe it or not, nobody has talked about this reveal, and which is basically what are the governing rules. What rules should you use if you build a consensus system from the bottom up? It's all hidden inside those algorithms, but it's not explicit, and I'll make it explicit for you. But before I begin, we have to talk about what is the external contract of a consensus protocol. Like, if I'm using a consensus protocol, what should be its behavior when I look at it from the outside, right? And as you know, Paxos is a single decree system, not very useful for real life. Raft is a replicated log, very useful, which is why Raft is immensely popular. So in here, you can see that in a consensus protocol, you give it a request, and the consensus protocol says, yes, I got your request. It means that it has saved your request in a log, and it will not lose it. The box that you see here, the round that you see here, is a full consensus system, which has multiple nodes inside it. Okay? And then you say you give it a request B. What it does is it appends that request to the log and returns success, and says and records B as having happened after A. So far, so good. Very simple, right? So basically, consensus system works as if it is just one system. So here is the time when it becomes complicated. How many of you have gone to shopping clicked buy and it starts spinning. And then you don't know what happened. So that is, and what do you do after that? You don't click again, right? You kind of go and see, did they charge my card? Did the sale happen? You do all the verifications and then come back and say, okay, I click again, or okay, I've got the product, right? So consensus system actually follows the same protocol. You give it a request, and if it does not respond, then the outcome is ambiguous. It's up to the consensus system to decide what to do with that request. It can do any of these things. It can either say, I've lost your request, you have to retry, or it can say, I have accepted your request. And how do you know it is accepted or not? You give it a second request. By the time the first request is A, by the time B comes as a request, it needs to make a decision whether to accept A or throw it away. If it accepts, then B happens after A. If it threw it away, then B is the first incident. Why is this important? This actually is the foundation of consensus protocols. The reason is because under the covers, this is a large number of nodes. And when there are failures within these nodes, you are going to be seeing a large number of failed things in flight. And how do you decide, authoritatively, what do you do with those requests that you see? Do you honor them? Do you throw them away? Did they become durable? So at that time, you can always go back to this specification and say, okay, is there any way that the system acknowledged the request as having completed? If the system acknowledged the request as having completed, then you don't have a choice. You have to honor it. But if it had not acknowledged it, you have a choice. You can say, you know what, I'm going to throw it away because I know that it was not acknowledged. So it's all based on this one fact. So I'm about to do the reveal. So in order to gain an intuitive understanding of a system, what you have to do is you need to understand its governing rules. And if I asked any of you, do you know what are the governing rules of Paxos? Do you know what are the governing rules of Raft? Would anybody be able to tell me? Right? You can explain the algorithm. You know that you can explain why it works. You can explain why it breaks, but you cannot explain its governing rules. So here are the rules. So before the rules, again, one more slide. I need to give you some definitions. What does a consensus system do? A consensus system executes a series of consistent distributed decisions. That is the job of a consensus system, like Raft. Right? What is a decision? It could be anything, but essentially a decision are transactions or requests that people send. And they change the state of the system. And who makes these decisions happen? I call them agents. So this is kind of very generic. So in other words, in Raft, a leader would be a typical agent because a leader executes requests. A leader is an agent. As an agent, it receives requests and makes them durable, writes them to the log by making them durable. So far, so good. Okay, now the rules. The first rule is the rule of durability. Every decision is a distributed decision, which means that in a consensus protocol, when I receive a request, that decision has to be made distributed and durable. The second rule is the rule of consistency, which is the decisions must be applied sequentially. So these are the two foundational rules of consensus protocols. Looks really, really simple, but it is not, and I'll expand. So this is not the full set of rules, but these are the two foundational rules. There's expansion under each of these rules. So let's drill down on the first one, right? The first one, a distributed decision must be made durable. So in other words, when I receive a request, my first job is to make sure that that request goes to all the places that are needed to make sure that the requests I received has become durable. Once durability has reached, I have the right to apply the decision. Like if I get a commit, I send the logs to all the places. Logs have gone to all the places. Now I can commit the transaction and then send the user, your transaction is committed. So this is a fairly simple rule. That's what consensus is. So any questions so far? Am I going too fast? Okay. Here's an example of how rule 1 is satisfied. Rule 1 is very easy to understand if you read the Raft protocol. So I just have an animation. So the application send a request A to a node. This is, we are looking at a 3-node majority-based consensus protocol. Oh, is it over? That's fine. And so the app sent a request A. Node 1 says, okay, I'm going to send it to the log. You can see that on the left-hand side, there's a applied line, which is basically the line that says, I've not applied this transaction yet. I've just recorded it in the log. Right? And then the node says, let me broadcast it to all the other nodes. The other nodes receive. They also record it in their logs. So far, nothing has been applied. And the app is still waiting for a response. And then the nodes respond saying that I got your transaction. And after they respond, then N1 says, okay, now I'm going to apply this transaction and then acknowledge to the app saying that, yes, your transaction will never be lost. So that is basically the guarantee that N1 gives. So if you look at this, right, this, so now after this, if I send a request B, it will be appended after A. If you look at the rules, both rules number 1 and 2 are satisfied. Right? It made the decision distributed, completed it, applied it, and then subsequent requests were appended to a log. By the fact that they were appended to the log means that they were made sequentially. So both rules 1 and 2 are satisfied. And so this is a full consensus system, except N1 may not remain the leader forever. There may be a failure, and we need a failover. So this is where the beauty of rules 1 and 2 come into play. No matter what you do, every operation that you do in a consensus protocol follows these rules. You just implement them differently. And every time you implement any kind of change in a consensus protocol, all you have to do is follow these rules. So here is the thing, right? So if a leader fails, what do we have to do? We have to appoint a new leader, right? If N1 has failed, we say I want N2 to become a leader. How do we make sure that we do it safely, right? If you go to Paxos, it'll say, start this proposal, start this term, and all that. Well, I'm a software engineer. How would I change leadership? Oh, maybe I'll tell N1 to stop accepting transactions. And once N1 has stopped accepting transactions, I'll tell N2, no, you're the leader. And I'll tell N3, you listen to N2 now. And start accepting transactions. Will that work? That'll work, actually. I followed all the rules.
Except split brain situations, right?
I've already told N1 to stop accepting transactions.
Did you tell N2 and N3 to stop accepting requests from N1?
They don't have to because they are currently accepting requests only from N1.
And N1 stopped sending those messages.
N1 is not sending any more requests. Who is I? It could be any agent, an external program that does this. Right? This doesn't look like Paxos. This doesn't look like Raft. But it's a completely valid consensus operation. Nobody does it because Raft and Paxos don't do it, but this is a very valid operation. An external agent comes and tells N1, please step down, make sure you send all your transactions, make sure they've all received it. N1 is not accepting any more transactions. And then told N2, you are now the leader, start accepting transactions.
We did something like that, or I did something like that. And sometimes you don't succeed in telling N1 to stop being the leader. And then
Exactly. Yes. So the caveat here is that this doesn't always work, right? You may not be able to reach N1. What if your network partitioned, right? What if N1 is dead, right? Or even worse, what if N1 is non-responsive? If it is non-responsive, you don't even know if it is down because it may later accept a transaction, right? So here's another scenario, right? N1 is not reachable. How do I tell N1 to step down? How do I prevent N1 from accepting any more transactions? You can implement a?
You
can implement a heartbeat in N1 to reach the
Heartbeat doesn't tell you to stop, right?
even to controller.
Yeah, but you have to tell N1 to stop accepting transactions.
It actually should be done on N1 level, and it should detect it's actually split brain between like from other nodes separate and shut down itself. It's like network equipment. Like
Correct. Yeah. So that's like if N1 is not able to. So that's one way to do it, right? You give it a lease, and then if it cannot get the necessary heartbeats, it just steps itself down. But what if N1 is able to complete, but you want to revoke N1's leadership? Yes.
It's tell N2 and N3 to stop accepting anything.
Yeah, I was waiting for that answer. Yes. You tell its followers to stop listening. If you tell N2 and N3, please don't accept any more transactions from N1, N1 cannot complete any requests because it'll try to send it and it won't get axed back. And therefore, N1's leadership is indirectly revoked. So in this, I quietly slipped in a concept that does not explicitly exist in Paxos or Raft, but is very much there, which is concept called revocation. So in a leadership system, when you want to change the leader, the first action that you must perform is revoke the previous leadership. So you revoke the previous leadership, and then you go and say, okay, now that I revoked it, now if you go back to the specifications of consensus, you revoke leadership, and then what you do is you go find out all the transactions that the leader might have completed. You find all the transactions that the leader has completed and make sure that they are propagated to the new nodes that are still surviving. And once you've done that, you find out who can be the new leader and then tell that person, you are now the leader, everybody else follow that leader, and you continue. So the question you have to ask yourself is, why do we do that, right? Why do we do such a thing? It's because we are subconsciously following rule number 2. What is rule number 2? Is every decision is sequenced, is one after the other. Yeah. So the first time you read Paxos, it kind of feels chaotic, right? Like a whole bunch of people are all coming together, proposing changes, conflicting. And if you look deep into the algorithm, what the algorithm is doing is just making sure that there is only one decision maker at any given point of time. And until they are not able to make any decisions, there's somebody else who tries to make their own decisions. The first time that a person makes a decision, then that decision becomes final and can never be changed. So that is a kind of what consensus is all about. So here is one thing about Postgres. So we are working on making Postgres, making Postgres follow consensus protocol. In Postgres, there is something called the full sync replication. The way full sync replication works is, oh my God, time flies. 10 minutes? Okay. Postgres accepts a transaction, and then sends it to the replicas. The replicas receive the transaction and apply it immediately, and then send an ACK. Then the primary also applies the transaction. This actually breaks rule number 1. How does it break rule number 1? Let me go back. So rule number 1 is a distributed decision must be made durable, and then it can be applied. Unfortunately, in Postgres, the decision is applied before it is made durable. How bad is it? It's actually not really that bad. All that means is that we have to rewind in a few cases. So if you find that some database has gone ahead, you find out and say, okay, you rewind. That's why there's a tool called PG Rewind, because these corner cases exist in Postgres, and the only way out is to rewind. So that's why PG Rewind is so popular. Okay, back to the slides. Okay. So this revocation and establishment of leadership is actually a sub-rule of rule number 2, right? But rule number 2 is actually a lot more generic. This revocation is not something. In this case, I made the problem intentionally simple. For example, the primary is reachable, right? The leader is reachable. If the leader is not reachable, how do you do it? There's another problem where yes, the leader is not reachable, or rather, I'm starting the failover. I've told you to step down, and I've promoted another leader, and that failed. And that leader did a few things, and it failed. And then there was a third agent that came, and that third agent did a few more things, and that also failed. When multiple failures like this happen, how do you know what is the truth? Finally, you go back and figure out, like what happened. How do you find the truth? And that is where rule number 2 becomes really, really complex. So that's the reason why I've split up the rules into 2 parts. The first part is every agent. It doesn't matter. There can be multiple agents that are trying to do this failover. My job is, as an agent, is to revoke all previous agents from doing forward progress. And if I've done that, then I have the right to do whatever I want to do. So if you, the hint here is the Paxos proposal number or the raft term number. That's exactly what it does. When a raft does a begin term, what it is essentially doing is revoking making all previous terms invalid, which means that nobody can do anything using the previous term number. So there's actually a corollary to that statement, which is if I am able to revoke previous terms, I have to provide a way for future people from revoking what I do, right? Because the reason why this means is typically when you do an algorithm like this, your tendency is to say, the first person that attempts to do something wins. The problem with the first person attempting to do something wins is, let's say I start attempting and then I go to sleep. How can somebody else come and stop me? Say that, you're dead. I need to take over from you, right? If I say I win, then I win. Then nobody can take it away from me. So that's the reason why every agent that does an action has to provide a way for a future agent from revoking it. So that's an inference. And the next part B becomes super complex. So for that, what I'm going to do is going to call on some volunteers to quickly come to the stage. I'm going to call Deepthi. Where's Tejas? I need to have Tejas come on. And I need 3 more people. Okay, come, you come. 2 more, you come. 1 more. Okay, there you go. Cool. Okay. I need a mic. So we are. We are going to do some live consensus. Let's keep it simple, right? Majority protocol, 5 nodes. 5 nodes. 3 is majority, right? Okay. I was going to do like, turn around, and you don't have time for all that. So I'm going to give you number 1, and you're going to try and distribute it to all of them. You're all number 0 right now. Let's say you just gave it to him. Okay, you have 1. Okay, that's it. You went dead. So no, you keep it. She's the leader. You're not allowed to act. You're just allowed to remember. Now I come in saying that, oh, this system is stuck. And I'm going to figure out what to do, right? And I say, scenario 1, I find these 3 people. What numbers do you have? 0, 0. You know what? 0 looks good. You are the leader. And I give you 2. Okay? And you are 1. You give it to him, 2. You are 2. Okay. Now there's 2 people with 1, 2 people with 2. And yes, we are stuck now.
Isn't the first leader dead?
But I still have the 1 record.
She's not lost. She's just non-communicative. Let's see. So there's 1, 1, and 2, 2. And now I am going to choose you, and you, because Tejas also has become non-communicative. So you have 1, you have 2, and you have 0. What should my decision be?
Roll everything back.
Well, the correct answer is I'll choose 2.
But on what basis? How do you know to choose 2?
I will explain why. Why is because when I chose, so this, we are talking about, let's also use these numbers as ordering,
Okay.
right? The fact that I know that 2 is a newer decision means that 2 is a safe decision. It is possible, like for example, when I gave it to you and I gave it to you, it is possible that you might have given it to Deepthi, right? Because you have the right to override her, because you are the newer decision, which means that if I see decision 2 and decision 1, 2 is a safer decision. So I can propagate 2.
Let me ask a question.
Yeah.
When you saw 3 zeros, why did you give one of them 2 and not 1?
It's a new decision. Like I say, I've basically elected Tejas as leader, opened him up for traffic, and somebody said 2.
Somebody said 2.
Yeah, some requests coming from the outside. Applications are sending requests. So application sent you request 1, and application sent him request 2. So far, so good?
So 2 is communicated as the act to the end user without being a
No,
decision?
in this case, no. Why? Because you didn't reach majority, right?
Yeah.
You gave it only to him.
So what is 2? So like you said that the 2 is the so you give him the 2 now? Like,
Yes, I have to decide now. So I'm deciding. So I see 2, 2, and 1. You are 0. So I can say, okay, now you are leader, propagate to everywhere else. So we'll stop here. So yeah.
Why are we using request numbers and not ABC? Because request numbers apply ordering.
Ordering. That's why I was using numbers. Yeah.
So there is ordering.
There is ordering. Ordering is very, very important.
From the client side.
From we call it request number 2.
Okay. So it's just request A, request B. Request B was created after request A. You know that somehow.
Correct. Yeah.
And you're using it's created later.
Yeah.
To determine which one wins.
Correct.
Sure.
So yes.
The ordering is important because the rule to we apply sequentially. So this ordering
correct. Yeah. So I went a little fast. What I should have done is I should have explained my reasoning, right? So when I reached these 3 people, and I saw 0. I had no doubts, right? Like anything else doesn't exist. So let's reset everything. Everybody is back to 0, right? Now you are 1. You are 1. Okay. In my discovery, let us say I find him, and him, right? 1, 0, and 0.
So those two are non-responsive?
He's responsive. He is not responsive. Tejas is not responsive. He has 1, he has 0, and he has 0. So when I look at this 1, what do I know? What can I infer, right? So this was your question. So because I cannot reach Tejas, I don't know Deepti's value or Tejas's value, right? But I cannot assume anything. They may have 1. He may also have 1. Deepti might have given Tejas 1. In that case, it has reached majority, which means that when I see his 1, I am afraid that this transaction might have completed, right? Because if Deepti had given it to Tejas, she might have acknowledged to the caller that this thing has completed, right? So my only safe decision is to honor this 1. If I had reached all 4 of them and not Deepti, I can say, oh, I know this 1 did not complete because only him, the only other person who could have it is Deepti. Yes.
So when the durability is in doubt, you're going to honor the decision, but you also need to ensure that the durability is no longer in doubt?
Correct. So that's the thing called propagate. So when you discover a decision, oh, we are out of time. When we discover a decision, I'll take 2 more minutes. When we are out of, when we discover a decision, I have to figure out how to. Can you repeat the question?
Yeah, you're unsure about the durability of a decision.
Yes, yes. I have to propagate it. I have to make sure that that decision becomes durable again before this thing. Yes.
So you are out of time in a logic and a metaphorical sense.
Thank you all.
Where is time in the rules? Right, because the implication was that again, the 0 and 1 and 2, we have this deep, intuitive, strong human sense of ordering, whether it's by clock or by time or by alphabetical ordering. So I was making sure I understood in the rules, where did you have clocks? Right, is this going to be appealed to a vector clock, or are you actually trying to make sure that this is a promise that doesn't involve accidents of time? Because for all we know, decision 0 happened after decision 1. And
correct, yeah.
One is in 3 places, one of them is non-responsive.
The simple answer is there is no clock used in this case, except for before and after. This happened before and that happened after.
The
causality
was exactly where these things break down. So I guess we'll keep listening.
Correct. Yes, yeah. So I'm out of time. So the only thing I can do now is we have actually made this work in Multigres. This protocol, I don't have a demo. The demo is uninteresting. All you can see is, if there's a primary that fails, it immediately elects a leader and continues. The difference is that our durability is pluggable, which means that those scenarios that I showed you, you can give that as code to Multigres, and Multigres will honor, will make consensus work for those rules. We use synchronous replication. The protocol is very different from Raft or Paxos because we have separate coordinators. But we do use Raft-like turn numbers. The most important of all is we can guarantee theoretical correctness. We can guarantee that we will not lose your transactions because there is proof behind these things. And the last one is Multigres HA is batteries included. So an HA system doesn't work in a vacuum. Just like even though the Raft is that way, you need a backup system. You need a system that forwards traffic to the right primary. And so it's good to have all of those. So we have implemented that also in Multigres. And we'll be actually be posting demos in our blog. So be on the lookout for those. And thank you very much. I'll be available for questions later.
Thank you very much. Unfortunately, the end of time marches onwards unceasingly, and we have to cut it a little short, but that was amazing.
If you can prove that, you've got everything else solved.
Yeah.
Oh, I don't want a keyboard. Or is that the?
Just it's just for the clicker. You can just close it.
Great.
And
then I'm fine mirroring.
Yeah, mirror is good then.
Oh, I'm already mirrored, so maybe I don't need to do anything.
Oh, yeah, that's good.
I'm fine with that.
Okay, so this microphone, clicker here.
Yes.
All good?
Thank you. Yes. Thank
Give
you.
it up.
Hello. That works. Cool. Hi, I'm Stu. I'm from ParadeDB. And today I'm going to talk about how we implemented top K joins in ParadeDB. Longer subtitle is Inverted Indexing and Analytical Planning for Sub-Second Relational Search. I think all those words will make sense later, hopefully. What is ParadeDB? ParadeDB is an Elasticsearch alternative built as a Postgres extension using TANTV, which is a Rust full-text search library that basically cloned Lucene, unapologetically cloned Lucene. We are full-featured, meaning we have most of Elasticsearch features, which is an incredibly long list. We have 80%, we have the 80%. We are fast, competitively fast with Elasticsearch, and we're easy to use in the sense that if you are already using Postgres, we can just be an extension inside of your database, but also you could hook us up as logical replication, leave everything normalized the way it is. So we're focused on full text search over OLTP schemas, right? We're not focused necessarily on generic performance for all of the TPC-H queries that you might want to run. We're focused on those very low latency top K queries, right? But what it means to be relational search is you have a normalized schema. You're in Postgres, so you have tables. You've modeled things appropriately the way they taught you. That means joins are essential, and that's what this talk is about. We adopt OLAP techniques to do that very low latency top K, and top K is, the good example is you're on a shopping site, you search for something, you get the top K results. It tells you that there are a few million more results, right? That's an aggregate that it's doing. On the left-hand side, it's also doing an aggregate to tell you which brands are available, right? So those aggregates there are search aggregates or facets, right? This talk today, though, is not just about top K joins. It kind of talks about the independent evolution of search systems and OLAP systems toward very similar architectures, right? This is one of those everything turns into crabs argument, right? Search systems and OLAP systems have trended towards similar places. So how does that impact the design of top K joins? So we have these two paradigms. So the analytics paradigm, the key word in analytics, I would say, is vectorization. You can obviously generate code as well. And so there's a school of thought that you should generate code to get your very tight loops. But vectorization is about doing things on much larger batches. And so all operators process dense columnar batches, e.g. arrow. So DuckDB defaults to 2,000 rows. Data Fusion defaults to 8,000 rows. And you tune that batch size to overcome the interpretation overhead. For example, if I had one row in my batch, I'd spend a long time switching batches, deciding what to do with each batch. These batches end up being CPU cache sized. So we'll talk about that a little bit later. And then file formats end up sized and tuned for this paradigm, right? So Parquet, you store on disk some multiple of your batch size, right? We'll get into that. A critical part of the analytics paradigm is late materialization, which effectively just means fetching column values as late as is reasonable. We'll get into that later. And so if you can apply a really selective filter that's going to throw away a ton of rows first, and if you aren't going to then have to access your data in some ridiculous random order, right? Like in reverse order or randomly coming back to a block multiple times, then it can avoid IO and CPU to just defer it, try to do it later, fetch that column later. Late materialization is a spectrum though, right? At the very top of a query plan, that's pretty late. That's after all the joins and the top K filtering have happened. You don't have many rows left, right? So but the rows that are left are probably randomized, right? Maybe you've gone through a hash join and something, and so the results are going to be in some other order. And you've done the top K filter, so now they're they're in that order. You're also probably fetching all the columns. In the middle, maybe you're applying indexes. If you have secondary indexes, closer to the middle of your plan, still above the scan, you have an external source of a row pointer. And now I need to go my table and get this pointer, right? At the very bottom, you can still do late materialization in the sense that if I'm fetching multiple columns out of a Parquet row group or out of a column store, I can visit them in some order and I can apply the most selective filters first and say, oh, all these rows are eliminated. I'm not going to fetch, I'm not going to decompress or do whatever with the other columns for those rows. And a point is dynamic filtering. Dynamic filtering is the idea of somewhere up in your plan, pushing a filter down to lower, right? As data flows up, push some information down based on information higher in the plan. I know I'm not going to need this anymore. Please don't send it to me, right? Please stop sending me this. There are good blog posts about this for Parquet. Okay, let's talk about the other paradigm. So the search paradigm ends up being somewhat similar, right? Independently evolved toward a similar columnar layout. There's a column store, and the columns in there, for example, in this case, if this is a string column, it has term IDs, which are very compact, impressively compressed, integers. And then the much larger string data is generically compressed off to the side. Same goes for a dictionary for a posting list. And a posting list is an index that is intersected. I'll show you on the next slide. These are broken up into multiple segments. I'm not showing that here, right? But you kind of think of this as an LSM tree where you have a few different segments and you merge all of them when you want to do a query. This format is inherently biased toward random access, right? The posting lists, after you've intersected them, act like a bitmap index. And so you can go to the column store for like one column. I executed my entire intersection and the result was one doc ID / row ID. So I'm going to fetch just that value from the column store. And so anyway, we'll get to that. In search, those posting lists are intersected, and they're intersected using a technique called block max weak and, which is primarily used for doing top K on a score. And the idea here is that the metadata at the head of the posting lists can be used to skip blocks. So if the block's maximum contribution to a score can't bring the block or any of the values in the block into your top K, you don't need to decode it. So you skip it. You kind of use this as a skip pointer into the next block, and that the header of the block also tells you how long the block is. These blocks are sized to be SIMD register size aligned and to allow skipping past, right? So there was a very influential paper, blog post and paper in 2012 by Daniel Lemire. And then block max indexes was the block max weekend paper in like 2009-ish. Lucene didn't end up picking it up until like 2017 or something. But the point is, you have 128 32-bit doc IDs in a block. SIMD BP 128 is 32 SIMD register operations with 128-bit registers, right? So you kind of flip the numbers. This means you're very SIMD aligned here. Okay, so how do these get mashed together? So this is the block size U curve for analytics. This, independently, the first talk at the bottom, or not talk, the first paper, PhD thesis at the bottom, was 2009 based on MonetDB. The second one is much more recent and is the one that Andrew told me to cite instead. So cite that one. The graph is a little better. They both look the same, 2009 and then 2018. It's a similar graph. The shape of the graph is that on the left-hand side, you're dominated by interpretation overhead. On the right-hand side, you start not fitting into your L2 cache anymore, right? And so you start cache thrashing. So that's why we're in the center here in analytics. Pivoting a little bit back to late materialization. So if you eager materialize, let's just talk about eager materializing. So you say you have 3 tables joined. It's 100 columns in the target list. You're going to fetch a ton of data. If you do not have top of plan, let's talk about this. You're going to fetch 4 million rows worth of target list, all of their columns, only to discard them at the very end to get 5, right? You really want to wait until the very end and use and load only what you need rather than loading the entire table. So you really want top of plan late materialization. Data fusion, again, without top of plan materialization, can only do marginally better than Postgres. Postgres is going to read the whole thing. It's a row store, so it doesn't have a capability to kind of read only one column, right? With top of plan late materialization, one way you can achieve that is you can write this as a CTE. The query's down here. If I rewrite it as a CTE, it kind of just barely fits on the slide, right? It's a lot of work. You don't want to have to do that, but if you do that, it's 20 times faster. And ParadeDB executes this 45 times faster, and by accessing 55 times fewer buffers, right? So too long didn't read. We really want top of plan late materialization. So a blind spot for analytics right now is that the effectiveness of top of plan late materialization, i.e. going back and getting those rows from the very tippy top, is bound by the storage layout. Fetching a single cell in Parquet by default is going to involve fetching and decoding a 1 megabyte page. It's a big multiple of this 8K row. And it might be using generic compression. So if you just want one, you still have to decompress the whole thing. Snowflake has micro partitions. They're a lot like Parquet, but then it has a cloud optimization service to make that great. Thank you for hosting us. ClickHouse typically relies on larger blocks and generic compression, but it does have top of plan late materialization. DuckDB has a good format. Lance and Vortex are great formats. ClickHouse and DuckDB implement top of plan late materialization, which is great. They actually have to disable it though if the file format is not going to give them good random access back in, right? And so DuckDB has the selective late materialization paper that's great. ParadeDB implements something similar to data fusion in this area. And so to make that visual, your page size is way the heck over there. It's some multiple of your actual optimal size. But if you're coming back for a single row, you still have to do all of that work. So blind spots for search. Search engines typically lack relational optimizing planners. You usually have a static query interface, which is basically just giving you an iterator over points, and then a collector, which is going to consume the iterator. And so this is not, if you're used to a relational planner and being able to move where you're loading data and then keep it loaded all the way through until later in the query, you can't do that, right? You just end up double decoding things, right? It's not particularly flexible. And late materialization is kind of required rather than tunable. As I said, you can't load it earlier and then keep it through into collection. Additionally, despite kind of evolving in the same direction to get incredibly low latency queries for faceted search, the column storage in search systems is usually a little immature. It's a few years behind, I would say, behind the open analytics formats. But this SIMD aligned access that it's doing is on this other side of the spectrum, right? Why? The reason is that because it's SIMD aligned, it can actually make more sense. Because it's SIMD aligned and sparse, right? You're able to skip decoding data at a block size, or not at a block size, at a block size that is significantly lower than the analytics default, right? Even though you begin to tip up here, if your search is sparse enough, you're skipping a lot of data, and so you're decoding less overall, and it ends up being faster. And as a case in point, Lucene is currently experimenting with a 256 row block, because AVX 512 is pretty widely available now. But it actually has mixed results, right? It's going to take a little while to dethrone 128 row blocks. Okay, so my broad generalization for this portion of the talk, analytics is probably too focused on computing filters inside of the row group, right? And search is probably too focused on computing filters outside of the row group, by which I mean, analytics is currently a little bit too focused on bottom of plan late materialization, right? Parquet, I'll get to why. And search it does not have block metadata to allow it to do good filters inside of a row group. Okay, so let's talk about ParadeDB's top K join architecture in this context. So this is a different query, a more interesting query perhaps. It's a semi-join filter against a list of IDs, and then top K on a string column, right, which is important here. Our goal is to do this really quickly. And I didn't really get into this earlier. ParadeDB is already very fast on a single table, right? That's table stakes. You have to be very fast on a single table. Elasticsearch is very fast on a single table. Being fast with multiple tables is kind of new terrain. And so that's why we're having to push a little bit harder here. The common knowledge is that, oh, you must denormalize to get fast search. We'd like to, if not prove that wrong, then at least raise the ceiling quite a bit, right? You can stay in Postgres without, totally mangling your schema for a nice long time. So anyway, baseline in Postgres is 1.7 seconds for this query, and it's eagerly fetching all of the rows. Postgres is also responsible for the join, and it's going to do that join row-wise on fully materialized columns. So what we do instead in ParadeDB is we are a Postgres extension, as I mentioned. We implement 4 or 5 of Postgres's extension hooks, and then are also an index access method. I could talk a lot more about that, but we translate the quals, which are basically the where clause, the target list, the joins, the order by, et cetera, everything, and push them down. The quals end up applied by TantTV's inverted indexes. An inverted index is not just a full text search tool. It can also be used for any sort of equality filter, right? So you can implement all equality filters as basically just intersections of all the posting lists. Range query is a little more difficult, but that comes out of the column store, right? That needs support for scanning the columns. We also implement dynamic filter push down to do the bottom of plan, late materialization. And then we implement a series of data fusion logical and physical optimization passes, which we'll go through. So at the bottom, we're doing that posting list intersection. Columns that are not involved in the join expression are not materialized, right? Late materialization. What we hold on to instead is a row pointer, i.e. a doc address, which is, we have done nothing other than record that this row is potentially interesting for later. We haven't loaded any of its columns, so we just have an integer. We might also have a partially materialized string, which is basically, we have a term ID. We don't know what that term ID refers to in the dictionary. It's just an integer. The dictionary is sorted. When we actually want to know, we can go and fetch it. We might have that if we've been applying dynamic filters, right? Way up in the plan, they said, "Oh, I've started to see some of the limit, and here's what my current threshold is." So you definitely don't need any columns that are going to be less than this threshold, right? We don't fully decode the term for that though. We just translate the filter. And then you're going to do a column-wise hash join. Again, this is not a row-wise hash join, column-wise hash join. The hash join ends up eliminating 92% of the rows. We support sorting the index, and so you might get a sort merge join instead. The next interesting thing in this plan is that we do predicate pull up, right? Not predicate push down, but predicate pull up. Why? Postgres indexes require MVCC visibility checks for every tuple. And how you execute that is by doing a heap block level visibility map check, which is just pretty cheap, but you have to require a lock on that buffer. But if you're stale, if the visibility map is stale, you actually have to fetch back to almost fully fetching a tuple from the heap, which is terrible. But the other problem is this is rarely a selective filter in a healthy table, right? You should have vacuum running regularly. And so maybe you should have like about 1 million out of a fairly large or fairly small fraction of your rows actually invisible, right? And so what we do is predicate pull up, right? Let's not apply this at the very bottom. Let's apply this as late as we can safely, right? And so you can pull a predicate up through the preserved side of a join. So we pull it up through hash join. And this defers not just the visibility check, but also getting the heap pointer, right? The CTID that we need to go and get that tuple out of the heap. We don't have to load from the column store. And so in this case, that means rather than loading 1.4 million CTIDs and visibility checking them, we do it much later after the join, and we only have to check 104,000, right? Finally, the top K itself. So I mentioned that we were deferring the decoding of all the strings. So what we do is these segments that I mentioned much earlier, they're pieces of the index that each have their own dictionary. And so you can't compare the term IDs from different segments to one another. But you can take the apple and banana term IDs, 0 and 1, and say apple is before banana. That's easy. I can just do that with the 0 and 1 term IDs. So we have a copy fork. We have a fork of the data fusion top K operator called segmented top K, which is aware of those segments and does a top K per segment, which eliminates, you go from 104,000 rows down to 25 per segment, and you have dozens of segments. So this is a much smaller number. Then you finally decode them, right? And then above that in the plan, we have TNTV lookup exec, which is for any other columns that haven't been materialized for some reason. There aren't any here. So the result of all of this is that you fetch, 9 times fewer buffers because you've done a bunch of late materialization at the top of the plan. You've done predicate pull up to avoid fetching the CTID and doing MVCC visibility checking. You've deferred decoding of all the strings, so you don't have to go to the dictionary except for, the top 25. And it's 6.5 times faster, right? We're well sub-second. And this is still just, one machine, right? We're using data fusion. We are not currently a distributed database. Hold tight, we'll get there. What's next? Actually, I'm not going to talk about becoming a distributed database, not anytime soon. What we will do fairly soon is selective late materialization, which is from a paper last year, which is essentially making smarter decisions about where to late materialize. Because our file format is so incredibly biased toward random access, because search is in general, almost everything is worth late materializing. The exception, though, is that if you are randomizing the order, right, and a filter is not very selective, if I had 1 million before and I have 1 million after, but now they're in random order, that's not very helpful, right? So we don't want to try to push late materialization through low selectivity randomizing plan nodes. Another thing is, as I said, these column formats are very good, but Vortex and Lance are very impressive, and they have gotten the message in terms of random access, right? DuckDB's file format we also talked about as having great random access. And that actually, the selective late materialization paper was implemented in DuckDB, for example. So it would be nice to get standardization and not be on a column format that was essentially cloned from Lucene a while back. Very good, not as good as the cutting edge. And because Lance or Vortex, we would be preserving random access. The final kind of frontier thing that we'd like to do is aggregate score joins. So we have so far been talking about joins, but when we are talking about a score, we're talking about a score from a single table. And that works for a lot of cases. But if for some reason you were doing full text search on multiple tables, right? Which actually that very first join I showed you was very much one where you want an aggregate score. I simplified it a little bit here. Basically, you want to be able to rank all your results by score, but you might want to do it as a sum of scores from different tables, right? So this ends up being very similar to that block max week and, but instead of doing it inside of your blocks, you're then doing it via sort merge join. And then one of the interesting questions that gets to the core of this talk is, would you want to then maintain SIMD aligned block sizes, or would you want to be more CPU cache friendly, right? Because as your sort merge join is going, do you want to be able to seek ahead on each iterator at a SIMD sized granularity or at a CPU cache sized granularity? We don't know yet, but we're going to find out fairly soon. And there were some papers about this or in mid 2000s, I think. So conclusion. Is there a sweet spot? TBD. There's no single optimal block size, and you kind of have to make trade-offs between these, the SIMD optimal and CPU cache optimal. But it is clear that each of these systems has been highly optimized for one and kind of has a blind spot in the other direction, right? So making dynamic decisions during decode to move from SIMD to block size to CPU cache friendly. What does search need from analytics? So yeah, we need a query planner, and I think we're starting to get one, which is great. We're very excited. But also, search should definitely be incorporating more CPU cache size batches into collection and aggregation time. What does that mean? There is a constant in the TNTV code base and probably in the Lucene code base for the block size, and it is 128, right? Is there a constant for CPU cache sized? No, right? You know, it's a blind spot. It's not something that you're considering that like, oh, if I am ever like dynamically increasing the size of my batch, should I stop somewhere? And the answer is yes, but anyway. What does analytics need from search? We are probably not beyond indexes. That's a reference. I'm not gonna name names. We're not beyond indexes, right? I think that ClickBench has been too much of a focus. It doesn't have any joins in it, right? And so formats that don't have random access are going to be able to do well there. So anyway, so yeah, so late materialization, external filters like indexes, highly valuable, but only to the degree that your file format actually allows you to go back to get something. So thank you to the South Bay Systems organizers, to our hosts, Snowflake, to the researchers I cited, to LLMs, I guess, but to open source communities, our team at ParadeDB, and to you, thank you for hiring. Thank you.
All right, another amazing talk. Thank you to both of our speakers. All right, well, just wrapping up, we have the creature comforts, if you haven't found them already: food, water, bathroom. Beyond that, our speakers should stick around for a while for questions. We have the place until 9. Thanks for coming.
Process. Yes, I was